Picture this. You are driving down the fast lane of a packed interstate. You're doing, I don't know, about 75 miles an hour.
Right, just cruising along.
Exactly. And the ambient temperature outside is hovering right around freezing. So it's cold, but you haven't hit a pothole. Your EV's battery state of charge is sitting comfortably at like 60%.
Everything seems totally normal.
As far as you know, everything is completely fine. But then suddenly, your electric vehicle just cuts its available power by 70%.
Wow.
Yeah, the accelerator pedal suddenly feels like it's connected to absolutely nothing.
Oh, wow.
And what you don't know in that moment, and frankly what the dashboard isn't explicitly telling you, is that a computer just detected this microscopic anomaly.
Something completely invisible to the driver.
Exactly. It might be a tiny bubble of air inside a copper weld that was made, 5 years ago. Or it could literally be the chemical breakdown of the battery's electrolyte at the molecular level. But either way, the vehicle has instantly decided that giving you full power would risk a catastrophic thermal event. So welcome to the deep dive. Today, we are tearing apart the engineering architecture behind how modern EVs predict, diagnose, and intercept failure before it ever happens.
And this really is, it's the absolute cutting edge of automotive functional safety. I mean, we are moving so far beyond the old days where a check engine light meant, you had a fouled spark plug that you could physically unscrew and just look at.
Right, you could hold it in your hand and see the carbon buildup.
Exactly. But in a modern high-voltage power battery, the diagnostic landscape is essentially invisible. We are dealing with a living, breathing electrochemical system.
A living system, yeah.
Yeah, and it alters its behavior every single millisecond based on thermal loads, chemical aging, dynamic tower demands. It's incredibly complex.
And today, we are hyper-focusing our lens on the single most critical diagnostic threshold in that entire invisible landscape.
The big one.
The big one. It's an active diagnostic trouble code designated as P0AC4. And the strict engineering definition of that is battery pack high DC internal resistance, which sounds like a mouthful, but it essentially functions as the ultimate mother code for an EV battery's health, right?
It really is. P0AC4 is the line in the sand. When that code triggers, it means the direct current internal resistance, what we call the DCIR, has breached a mathematically defined safety limit.
Okay, so it's not just a suggestion.
No, it's the system recognizing that the internal bottlenecks, whether they're chemical or physical, have become so severe that pushing normal current through the pack will generate localized joule heating.
Heat that exceeds what the cooling system can handle.
Precisely. And that's how you get a battery fire.
So the mission for this deep dive is to completely unpack that bottleneck. We're going to start at the molecular level, decoding the electrochemical breakdowns that basically choke the flow of lithium ions.
The chemistry side.
Yeah, the chemistry. And then from there, we'll zoom out to the physical hardware failures, the microscopic manufacturing defects that turn into massive resistive loads over years of driving.
The mechanical side.
Right. Then we're going to get into the control theory, which I'm super excited about. The actual mathematical architecture the battery management system uses to calculate this resistance on the fly, because it's doing this in a crazy, noisy electrical environment.
It's doing millions of calculations a second. And we won't stop at the diagnosis either. We have to look at the fail-safe response protocols.
How the car reacts.
Yeah, how the vehicle manages that massive power degradation without, causing an accident on the highway.
Because dropping 70% power at 75 miles an hour is no joke.
Exactly.
Yeah.
And finally, we'll cover the exhaustive DFMEA design iterations, the robotic manufacturing controls, and the violently intense mass production validation tests engineered to ensure P0AC4 theoretically never happens in the first place.
Right, making sure the code never actually has to trigger.
Yeah.
Let's get straight into the root causes. I like to look at a high-voltage battery pack, like a highly calibrated, high-performance athlete.
Okay, I like that analogy.
Right, so when the internal resistance is low, the cardiovascular system is operating perfectly, power flows efficiently. But when P0AC4 triggers, the athlete is suffocating. There's a fundamental restriction in the system.
Something is blocking the oxygen, so to speak.
Exactly. And the first place that restriction occurs is in the chemical layer. Based on the sources we have, there are 3 distinct electrochemical failure modes to tackle here. Let's start with the most common environmental stressor, extreme cold.
Yeah, the low-temperature dynamics of lithium-ion cells are fascinating because, well, it's a temporary physical bottleneck, right? It's not necessarily permanent damage.
It's just cold.
Right. It fundamentally comes down to the activation energy required for ion transport and the actual viscosity of the electrolyte solvent.
Okay, viscosity, so how thick the liquid is.
Yes. The electrolyte is the medium, usually this mixture of organic carbonates like ethylene carbonate and dimethyl carbonate, and that fluid facilitates the transport of lithium ions between the anode and the cathode.
And as the temperature drops, the thermodynamic reality of that liquid shifts, right? We aren't just talking about a slight drop in efficiency here.
Exactly. The viscosity of that organic solvent increases exponentially as you approach freezing temperatures. It literally undergoes a phase transition, becoming incredibly thick.
Okay, let's unpack this. It's like trying to run through a swimming pool filled with thick honey instead of water, right?
That is a perfect analogy. The lithium ions, which normally shuttle back and forth with very low impedance, are suddenly fighting through this highly viscous fluid.
They're struggling to move.
Right. Mathematically, the ion diffusion impedance skyrockets. The rate of the electrochemical reactions at the electrode-electrolyte interface slows down dramatically because the charge transfer resistance increases.
So when the driver stomps on the accelerator in that freezing environment, they are demanding a massive, immediate, transient current.
And that demand hits a chemical brick wall. You have a high current demand, which we call I, attempting to push through a massive polarization resistance, RP.
And what happens to the voltage when that happens?
The immediate result is a severe transient polarization voltage drop. The formula is straightforward. The voltage drop equals I times RP. Because the electrolyte is so sluggish, the battery voltage sags significantly under the load.
It plummets.
Yeah, and if the battery management system isn't precisely calibrated to understand that this is a temporary temperature-induced polarization, it sees that massive voltage sag, miscalculates a high internal resistance, and boom, it throws the P0AC4 fault.
Wow. Okay, but the reality is cold weather is something the battery can technically recover from once it warms up.
Right.
The honey turns back into water.
Exactly. The phase transition reverses.
Okay, but the second failure mode in the chemical layer is far more insidious because it represents permanent, irreversible degradation. What happens when the athlete isn't just cold, but is chronically overheating?
Right, so high temperature operation, especially when combined with high C rates, and by that I mean aggressive rapid charging and high power discharging, that fundamentally alters the chemical makeup of the cell.
You're literally cooking the chemistry.
You are. At elevated temperatures, the delicate thermodynamic equilibrium of the cell just breaks down. The primary victim here is the solid electrolyte interface, or the SEI layer, on the anode, alongside the actual electrolyte itself.
Now wait, the SEI layer is normally a good thing, right?
Yeah.
I thought that forms during the initial manufacturing cycles to protect the anode.
It is essential. It's a passivation layer that allows lithium ions to pass through, but it blocks the electrolyte solvent molecules from reacting with the lithiated carbon.
Like a selective filter.
Exactly. But at high temperatures, this SEI layer becomes unstable. It starts to dissolve into the electrolyte, and then it forces the cell to reform it over and over again.
Wait, so it dissolves and rebuilds constantly?
Yes, and every single time it reforms, it irreversibly consumes active lithium inventory from the cell, and it consumes more of the electrolyte solvent.
Oh, wow. So it's essentially cannibalizing itself just to maintain its internal structure.
Precisely. And while the SEI is continually thickening and eating up lithium at the anode, you have electrolyte oxidation occurring over at the cathode interface due to all that high thermal energy.
It's getting attacked on both sides.
Right. And these parasitic side reactions generate gaseous byproducts and solid precipitates that literally clog the porous structure of the electrodes.
Like plaque in an artery.
Exactly like that. Ultimately, you reach a point of electrolyte dryout. The liquid medium is permanently depleted.
So wait, cold makes it sluggish, but heat permanently cooks it dry.
Yes. The ionic conductivity suffers a permanent drop, raising the ohmic resistance permanently. You can't just cool the battery down to fix this. The chemical pathways are fundamentally scarred.
That is wild. Okay, so that covers the fluid dynamics and the parasitic chemical reactions.
Yeah.
But the third chemical root cause is a catastrophic failure of the actual physical architecture of the electrodes themselves. LAM, loss of active material.
This is where we look at the mechanical stress induced by the electrochemical cycling itself. Think about what actually happens during a charge and discharge cycle. Lithium ions are physically intercalating. They're inserting themselves into the crystal lattice of the cathode and anode materials, and then de-intercalating.
So the battery is physically expanding and contracting. It's breathing.
Exactly. It's microscopic, obviously, but it is a violent physical volume expansion and contraction at the atomic level.
Okay, I can see where this is going.
Now, combine that constant mechanical flexing with massive thermal stress from high-power driving. Over time, the structural binders like PVDF that hold the electrode particles to the conductive current collectors, they just begin to fail.
The glue gives out.
Yeah, the active material literally cracks and detaches from the conductive framework. It becomes electrically isolated, it's in the battery, but it can't participate in the circuit anymore.
This is especially critical with modern high-nickel cathodes, right? We are seeing a massive push across the industry toward NMC 811, so that's 80% nickel, 10% manganese, 10% cobalt, mostly because of the incredible energy density. But that density comes at a structural cost, doesn't it?
Oh, absolutely. High nickel cathodes are incredibly energy dense, but they suffer from severe structural instability at high states of charge and high temperatures.
They're fragile.
Very. During aggressive cycling, the anisotropic volume expansion, meaning it expands unevenly of the high nickel particles, causes severe intergranular microcracking. The actual secondary particles fracture from the inside out.
Wow, so they're shattering internally. And that exposes fresh, unpassivated cathode surfaces to the electrolyte, right?
Which triggers violent localized side reactions all over again. Furthermore, this microcracking leads to transition metal dissolution. The nickel and manganese ions literally dissolve into the electrolyte, migrate all the way across the separator, and deposit themselves onto the anode.
Oh, man, which destroys that SEI layer we just talked about.
Exactly. It is a rapid, cascading failure of the cell's entire internal architecture. The active material is lost, the conductive pathways are severed, and both the ohmic and polarization resistances just spike by orders of magnitude. The battery is effectively dead at that point.
Yeah. Okay, so we have the sluggish cold weather electrolyte, the heat-induced drying and parasitic reactions, and the physical micro-cracking of the cathode structure. All three of those manifest mathematically as an intolerable spike in DC internal resistance.
Yes.
But let's pivot here. What if the cell chemistry is pristine? What if the internal architecture is flawless, but the macro hardware, the physical interconnections outside the cell, what if that is what's failing?
Ah, right. That transitions us perfectly from the chemical dimension to the physical hardware level bottleneck.
Because a battery isn't just one big cell.
Right. A high voltage pack is hundreds, sometimes thousands of individual cells wired up in series and parallel. The resistance of the entire pack is really only as low as its weakest physical connection.
The weakest link in the chain.
Exactly. And the primary method for connecting all these cells together is high-energy laser welding of the cell tabs to the main copper or aluminum bus bars.
Which you're dealing with hundreds of amps of current. You can't just rely on like mechanical pressure or a cheap low-temperature solder joint. You have to literally fuse the metals together. But laser welding dissimilar metals, like an aluminum cell tab, to a copper bus bar that is notoriously difficult because of their different melting points and thermal conductivities, right?
It is highly complex. The manufacturing process relies on what's called keyhole laser welding. The laser intensity is so incredibly high that it doesn't just melt the metal, it vaporizes it.
It turns it into gas.
Yeah, it creates a column of vapor plasma, a keyhole that penetrates deep into the material. The molten metal flows around this plasma keyhole and then solidifies behind it to form the weld seam.
Which sounds incredibly precise, assuming the factory conditions are completely static. But we know they aren't.
If the laser focal length shifts by even a fraction of a millimeter, or if the peak power fluctuates, and this happens if the flow rate of the argon shielding gas is just slightly off, the keyhole dynamics become totally unstable.
So what happens to the weld?
The vapor cavity can collapse prematurely, and it traps the shielding gas or the metallic vapor inside the molten pool.
Oh, so you get bubbles.
Yes. When it solidifies, you are left with microscopic voids, air bubbles inside the weld. Or, worse, you get what's called a false weld or a cold weld.
Where it looks connected but isn't.
Exactly. The metals are superficially touching, maybe lightly tacked, but they haven't achieved true metallurgical fusion.
So the battery leaves the factory.
Yeah.
It passes the basic end-of-line electrical checks because the metals are technically touching. The resistance looks totally fine on day one. But then you put this battery pack into a vehicle, and I mean, an automotive environment is essentially a continuous rolling earthquake.
High cycle fatigue is the absolute enemy of a false weld. The vehicle is subjected to constant multi-axis vibration from the road, and simultaneously you have the thermal expansion mismatch we discussed.
Right, because copper and aluminum expand differently when they get hot.
drastically different coefficients of thermal expansion, or CTE. As the battery heats up under heavy load and then cools down when it's parked in your driveway, the copper and aluminum expand and contract at different rates.
They're fighting each other.
Yes, and that induces massive shear stress precisely at that tiny, fragile weld joint.
It's cyclical loading. So over thousands of miles, that microscopic gas void from the factory, that little air bubble, acts as a stress concentration point.
Exactly. The void propagates into a macroscopic fatigue crack, and as the crack spreads, it severs the cross-sectional area of the weld.
It chokes it off.
The physical pathway for the current literally shrinks. It's like taking a multi-lane highway and abruptly funneling everyone down into a single lane.
A huge traffic jam of electrons.
The current density at the remaining intact metal skyrockets, generating intense localized joule heating. The resistance spikes dramatically, and the diagnostic architecture flags the P0AC4 code because it senses this massive physical bottleneck.
Okay, so laser welding clearly has its own incredibly complex failure modes. But there are still traditional mechanical bolted joints in a battery pack, right? Like the main high-voltage terminal connections, the connections to the contactors. Those are often heavy bolted copper bus bars and, well, bolts back out.
Bolted connections are highly susceptible to torque decay over time, but it's primarily due to a phenomenon called thermal shear relaxation.
Wait, so it's not just the vibration rattling the bolt loose?
No, it's not just vibrations spinning it. When you compress two copper bus bars together with a hard steel bolt, you are dealing with different material stiffness and, again, those thermal expansion rates. Over years of thermal cycling, the copper literally creeps and relaxes under the compressive load of the steel bolt.
The copper actually yields over time. It just gives way, reducing the clamping force.
Yes. The initial preload torque that was perfectly applied at the factory just drops, and once the clamping pressure falls below a critical threshold, the joint is compromised.
The connection gets loose.
And it's not just a loss of physical contact. When the joint relaxes, it allows ambient humidity and oxygen from the air to penetrate the interface between the two bus bars.
Which introduces fretting wear and oxidation, right?
Yes. Bare copper oxidizes very rapidly in the presence of humidity. And here's the critical electrical distinction we have to make. Copper oxide is a semiconductor bordering on being a total insulator.
It blocks current.
It is highly resistive. So as the bolt relaxes, a vibration causes microscopic rubbing, which we call fretting between the bus bars. This fretting continually breaks off fresh copper particles, which immediately oxidize.
Oh, so it just keeps building up more and more rust, basically.
It builds up a thick, highly resistive crust of copper oxide directly inside the current path.
And the contact resistance goes completely through the roof.
It creates a localized hotspot that can easily exceed 200 degrees Celsius under load. And that heat just accelerates further oxidation in this vicious positive feedback loop.
A downward spiral.
Exactly. The system sees this isolated, massive contact resistance, assumes the structural integrity of the high-voltage loop is failing, and it triggers the mother code.
Okay, I have to push back here for a second because we have just meticulously outlined two fundamentally different failure modes.
Right.
On one hand, we have freezing cold electrolyte driving up the polarization resistance chemically. On the other hand, we have a localized, rusted, vibrating loose bolt driving up the physical ohmic resistance.
Very different physics.
Exactly. But if I am driving down the highway at 70 miles an hour, pushing massive current, the only thing the vehicle's computer can actually see is a voltage drop, right?
No.
How is it mathematically possible for the control module to differentiate between sluggish chemistry and a cracked weld in real time, especially in a vehicle that is heavily polluted with electrical noise from the motors and inverters?
That right there is the core engineering challenge of the BMS, the battery management system. It cannot just rely on a simple Ohm's law calculation of voltage divided by current.
Because there's too much noise.
The automotive electrical environment is incredibly noisy. The traction inverters are switching at incredibly high frequencies, creating massive electromagnetic interference. To isolate the true DC internal resistance and accurately trigger P0AC4, the BMS relies on highly advanced control theory.
Okay, wait on me.
Specifically, it utilizes equivalent circuit models and adaptive extended Kalman filters.
Okay, let's break down that first one. The equivalent circuit model, the ECM.
Yeah.
How does the BMS create a mathematical twin of the battery inside its software?
An ECM is a dynamic mathematical representation of the cell's electrical behavior. It typically uses what's called a Thevenin model. You have a voltage source, which represents the open circuit voltage.
Right.
In the series with that, you have a pure resistor representing the ohmic resistance. We call that R0. This covers all the physical hardware, the bus bars, the welds, and the pure electrolyte resistance.
The instant physical stuff.
Exactly. Then, to capture the chemical polarization and diffusion effects, you add one or two resistor-capacitor branches, RC branches, in series.
And those RC branches simulate the time delay, right?
Yeah.
The sluggishness of the chemistry we talked about.
Exactly. Ochromic resistance, R0, responds instantaneously to a current change. But polarization resistance, represented by the RC branches, takes time to build up and decay. It has a time constant.
Because the ions actually have to physically swim through the liquid.
Exactly. By running this model in real time, the BMS attempts to predict what the battery's terminal voltage should be at any given microsecond, based on the current flowing through it.
But the internal resistance isn't a static number. It changes with temperature, state of charge, and aging. So how does the model update itself on the fly? This is where those Kalman filters come in, right?
Yes, the BMS employs recursive least squares algorithms, RLS, often paired with adaptive extended Kalman filters, or AEKF. A Kalman filter is essentially an algorithm that estimates the true state of a dynamic system from a series of noisy, incomplete measurements.
Okay, I understand the theory, but here's where it gets really dense. I've always questioned the computational load of running matrix inversions in real time on a vehicle microcontroller. Can we translate this? How does it handle the inverter switching noise without just constantly adjusting its model to chase false signals?
That is precisely why it is an adaptive extended Kalman filter. The filter operates in two distinct phases, predict and update.
Okay.
First, it uses the equivalent circuit model we just talked about to predict what the voltage will be. Then it uses the physical sensors to measure the actual real-world voltage.
And they usually don't match perfectly.
Right. The difference between the prediction and the reality is called the innovation.
And it uses that innovation, that error, to correct its internal model.
Yes, but, and this is the genius part, it doesn't trust every measurement equally. The filter maintains covariance matrices, which is essentially a mathematical measure of uncertainty.
It literally calculates how sure it is of itself.
Exactly. It has a process noise covariance representing how much it trusts its own internal math model, and a measurement noise covariance representing how much it trusts the physical sensors.
So if the motor is spinning up and throwing off tons of electrical noise,
Because the motor inverter introduces that high-frequency noise, the adaptive mechanism dynamically tunes these noise matrices. If it detects a high levels of electrical noise, it says, I don't trust the sensors right now, and it relies more heavily on its internal model.
wow. So it's constantly weighing its own prediction against reality, filtering out the noise and recursively updating the values of R0 and the RC branches.
Millions of times a second.
But to accurately isolate the true DC internal resistance, the algorithm needs a really strong signal-to-noise ratio, right? It can't just run an update based on you turning on the radio or the seat heaters.
No, the current draw is too small, which is why the strict diagnostic protocol for P0AC4 utilizes high current differential fitting.
What is that?
The algorithm doesn't make a definitive internal resistance calculation during steady-state cruising on the highway. The signal is just too weak. It actively waits for a massive dynamic load change.
It waits for you to floor it.
Specifically, it looks for a step change in current, a delta I, of at least 100 amps within a fraction of a second.
A 100-amp spike. That really only happens during heavy, aggressive acceleration or maybe max regenerative braking.
Exactly. When you stomp the accelerator to pass someone, you induce a massive, instantaneous step change in current. The AEKF algorithm immediately wakes up and captures the exact voltage sag, the delta V, at that exact millisecond.
Because it's instantaneous.
By analyzing the instantaneous voltage drop against the 100-amp spike, it completely isolates the ohmic resistance, R0, from the chemical polarization resistance because the chemistry hasn't had time to react yet.
Because of that time delay.
Yes, it fits the curve, calculates the true physical dynamic impedance, and records the value.
It is genuinely incredible that this level of control theory is running thousands of times a second underneath the floorboards while you're just commuting to work.
It's beautiful math.
But calculating the exact resistance is really only the diagnostic half of the equation. Once the BMS confidently confirms that the DCIR has breached the safety threshold, what does the system actually do? How does it manage the failsafe?
Well, the trigger threshold for P0AC4 is strictly defined in the functional safety architecture. It's a 50% increase.
50%.
Yes. The BMS continually references the beginning of life, or BOL, resistance baseline that was permanently stored in its memory at the factory. If the dynamically calculated real-time resistance exceeds that baseline by 50% or more, the threshold is breached.
A 50% increase is massive. I mean, that implies severe degradation or a truly critical hardware failure, like a nearly broken weld.
And the response must be immediate and completely deterministic. The BMS instantly registers P0AC4 as an active diagnostic trouble code in its permanent memory.
The check engine light comes on.
And simultaneously, it blasts a high-priority interrupt signal across the CNFD network, the controller area network flexible data rate bus. This is basically the central nervous system of the vehicle.
It's sending that signal directly to the vehicle control unit, the VCU, and the hybrid powertrain control module, right?
Well,
The actual brains driving the motors.
yes. The VCU is the master torque commander. When it receives that POA-AC4 interrupt, it immediately executes an SOP derating strategy state of power derating.
Okay, here we go. The limp mode.
The functional safety protocol dictates a level 2 derating, which rigidly clamps the allowable charge and discharge power limits down to just 30% to 50% of the battery's nominal capacity.
Okay, let me challenge this for a second. If the system has confidently diagnosed a 50% spike in internal resistance, we know for a fact that pulling current through that resistance is going to generate intense, localized Joule heating.
Uncontrollable heat, yes.
We're looking at a high probability of thermal runaway if it's a cracked bus bar. So why on earth does the functional safety protocol allow even 30 to 50% power? Why isn't the mandate a 0% immediate contact or open, a total system shutdown, to prevent a lithium fire right then and there?
It's a great question, and this is the central debate in ISO 26262 ACEL automotive safety integrity level classifications. You are basically balancing two catastrophic risks against each other.
Fire versus what?
The kinetic risk. The risk of thermal runaway is high, yes, but the immediate kinetic risk to the driver is higher.
Oh, I see.
If a vehicle traveling at 80 miles per hour in heavy highway traffic instantly opens its high-voltage contactors, you lose all propulsion instantly. The vehicle becomes a dead, uncontrolled kinetic mass.
You just be a brick on the highway.
The statistical likelihood of a fatal rear-end collision in a sudden loss of motive power scenario far outweighs the delayed risk of a thermal event, which, frankly, the cooling system can still attempt to manage at lower currents.
Wow. So the mandate is limp hum mode. You must provide enough torque for the driver to execute a safe lane change and pull over to the shoulder.
Exactly. It's a managed degradation.
Yeah.
But the VCU doesn't just instantly chop the power down to 30%. If it did that, it would cause a violent deceleration, a massive torque jerk, which could destabilize the vehicle dynamics, especially if you're driving in rain or snow.
So it eases the power down.
The DP rating is algorithmically smoothed out.
And there's an electrical necessity to that smoothing as well, related to the voltage limits, correct? Not just the physical jerk.
Yes, preventing an undervoltage protection, or UVP, shutdown. Because the internal resistance is so high, pulling normal current causes the terminal voltage to sag violently.
We talked about the voltage sagging earlier.
Right. If the VCU allowed a sudden current spike, the voltage could easily crash below the cell's minimum safe threshold. If UVP triggers, the hardware protection forces the contactors open instantaneously anyway, causing the exact total blackout we are trying to avoid.
It's a cascading failure.
By smoothly clamping the torque, the VCU prevents that deep voltage sag, keeps the system alive, and minimizes the localized heat generation at the fault point, giving you time to pull over.
It is a phenomenal balancing act of software and control theory. But, relying on a software degrading strategy means the vehicle already failed. The ultimate goal of automotive engineering isn't just to manage a failure safely, it's to design the physical hardware so robustly that the failure never occurs in the first place.
Prevention is better than a cure.
Which brings us to the design prevention phase, the realm of DFMEA design failure mode and effects analysis.
DFMEA is where the engineering teams sit down and systematically attempt to break their own designs in theory, on paper, and in simulation before a single physical prototype is ever built.
They're trying to find every flaw.
They evaluate every possible failure mode, they score its severity, its likelihood of occurrence, and the system's ability to detect it.
And in the DFMEA matrix, P0AC4 is assigned a severity score of 7 out of 10.
Which is huge. A severity 7 is extremely high for a fault that isn't instantaneously fatal. It earns that 7 because it inherently results in a loss of primary vehicle function, the loss of motive power, and because the underlying cause, that localized joule heating, carries a direct path to thermal propagation. Fire. Because it's a SESN, the engineering requirements dictate hyper-aggressive design countermeasures to drive the occurrence rate down to near absolute zero.
So let's look at the mechanical countermeasures for those bolted busbar connections we discussed earlier. We talked about how bolted flat copper bus bars suffer from thermal shear relaxation. They loosen up and they get high contact resistance. How do you design out the flaws of just bolting two perfectly flat pieces of metal together?
By recognizing that at a microscopic level, a flat piece of metal isn't flat at all.
What do you mean?
According to Holmes' theory of electrical contacts, when two nominally flat metal surfaces are bolted together, they only physically touch at a few microscopic asperities, the absolute highest microscopic peaks of the surface roughness.
Oh, like two mountain ranges pressing together. They only touch at the peaks.
Exactly. So the electrical current, instead of flowing evenly across the entire surface area of the bus bar, is forced to squeeze through these tiny microscopic bridges.
And that bottleneck causes heat.
Massive current crowding. It's known as constriction resistance. All the current bottlenecking at these few microscopic points generates intense localized heat. To combat this, advanced DFMEA requires engineered multi-point or micro-bump contact designs.
Wait, so they intentionally machine microscopic bumps into the surface of the copper?
Yes. Engineers use finite element analysis, FEA, and coupled electrothermal electromagnetic simulations to model the exact geometry of the joint. They design specific, highly uniform microbumps across the surface.
Why bumps?
When the bolt applies clamping force, these engineered bumps are designed to plastically deform at very predictable rates. They flatten out to guarantee a massive, evenly distributed matrix of true contact area.
They squish perfectly to make a solid connection.
Yes, and the FEA simulations push virtual thousands of amps through these computer models to ensure the current density vector field is perfectly uniform, which entirely eliminates localized constriction resistance hotspots.
That is wild. But even with perfectly engineered, squishy microbumps, you still have the issue of oxidation over time if the bolt relaxes even a fraction of a micron, right? You get that copper oxide crust.
Which leads to the material specification countermeasures. Bare copper is completely unacceptable in these critical high-voltage joints due to the insulating properties of copper oxide. The DFMEA mandates high-specification plating, specifically nickel or silver plating, over the copper bus bars.
Silver plating, I mean, silver is incredibly expensive for mass production. Why is it justified here?
Because of the tribological and chemical properties of silver. Silver is highly conductive, yes, but more importantly, if oxygen does penetrate the joint over 10 years and silver oxide forms.
Oh, let me guess. Silver oxide is conductor.
Silver oxide remains electrically conductive. It does not create an insulating crust like copper oxide does. It entirely neutralizes the occurrence risk of oxidation-induced resistance.
That is a brilliant material solution. Okay, so the hardware design is structurally robust, it's electrothermally simulated, and chemically inert. What about the software design? We discussed earlier how extreme cold chemically mimics high resistance.
A honey analogy.
Right. How do you design the software to be anti-false alarm so you aren't leaving drivers stranded in limp home mode every winter just because their battery's a little cold?
The BMS architecture utilizes massive high-precision 2D lookup tables, or LUTs, embedded deep in the software. This is basically a state space mapping of the battery's acceptable operational parameters.
So it's essentially a massive matrix of predetermined answers. A cheat sheet.
Exactly. The engineering teams physically characterize the battery cells in massive thermal chambers during the design phase. They map out the exact expected ohmic and polarization resistance for every single temperature degree, cross-referenced with every single percentage point of state of charge from 100% all the way down to 0%.
Every single combination.
Yes. So when the car starts up at negative 20 degrees Celsius on a Tuesday morning, and the AEKF algorithm calculates a massive internal resistance due to the viscous electrolyte, it doesn't immediately panic.
It checks the cheat sheet.
Right. Before the BMS triggers the P0AC4 threshold flag, it cross-references that dynamically calculated resistance against the 2D lookup table. The LUT verifies, hey, at negative 20 degrees and 40% SOCI, this mathematically high resistance is physically normal and expected.
So the software intelligently overrides the baseline threshold, entirely preventing a false positive.
It knows the difference between a broken battery and a cold battery.
Okay, so the theoretical design is bulletproof. The simulations are perfect, the plating is silver, the software has a complete state space map of the chemistry. But none of that matters the second you hand a wrench to a line worker on a Tuesday morning.
Human error.
Right. How do you force the physical reality of a high-volume manufacturing floor to match the perfect mathematics of the DFMEA?
That is the realm of PFMEA process failure mode and effects analysis. The focus shifts from the design of the part to the strict statistical control of the manufacturing process itself.
Controlling the factory.
The framework here is 5M1E, controlling man, machine, material, method, measurement, and environment. The goal is to entirely engineer out human error.
So if the root cause of the physical resistance is a loose bolt, you can't just mandate that line workers use standard torque wrenches and hope they pull hard enough every single time.
No, the PFMEA specifies smart tightening systems as a KCC, a key control characteristic.
What makes it smart?
In a modern high-voltage assembly facility, manual clicking torque wrenches are completely obsolete. The KCC mandates 100% servo-controlled electric DC newt runners. These tools don't just apply force, they measure the entire fastening dynamic in real time.
And the specific parameters are incredibly tight, right? The sources say the target torque is exactly 9.0 Newton meters with an allowable tolerance of only plus or minus 0.5 Newton meters.
Yes, but torque alone is a deeply flawed metric.
Why?
Because torque is simply a measure of rotational friction. If the threads of the bolt are dirty, or if the bolt is cross-threaded, you might hit 9.0 Newton meters of friction before the bolt head even touches the copper bus bar.
Oh, so the wrench clicks, but the plates aren't actually clamped together.
Exactly. Therefore, the smart tightening system utilizes a closed-loop dual-parameter check. It measures torque and angle,
Controlling the exact degree of physical rotation of the bolt.
The system monitors the torque ramp-up. Once it hits a snug torque, say 2.0 Newton meters, meaning the head is just touching the plate, it begins measuring the physical rotation angle. The bolt must hit the final 9.0 Newton meter target within a strictly defined angle window of, let's say, 30 to 45 degrees of rotation.
So it has to turn exactly that much to reach the final tightness.
Right. If it hits 9.0 nm at only 15 degrees of rotation, the system knows the bolt is cross-threaded or jammed. If it rotates 60 degrees and still hasn't hit 9.0 nm, the system knows the bolt is yielding, stretching, or it's stripping the threads out of the hole.
That is insanely precise. But if a factory is producing hundreds of battery packs a day and the tolerance is that tight, what happens when a bolt inevitably falls outside that 30 to 45 degree window? Does a red light just flash on a screen somewhere?
It is far more draconian than a red light. The servo newt runner is digitally bound to the factory's manufacturing execution system, the MES. The tightening data is recorded and tied permanently to the battery's unique serial number.
So there's a paper trail.
A digital one. And if a single bolt fails the torque angle curve, the MES automatically and physically locks down the assembly line.
It stops the entire line. Over one bolt, that is a massive throughput bottleneck for a factory.
It is a necessary functional safety bottleneck. The physical pallet carrying that specific battery module cannot advance to the next station. The MES interlock requires a designated quality control supervisor to physically walk over to the station, scan their ID badge, evaluate the rejected bolt, replace it, and oversee the manual retorquing before the line is unlocked.
Wow. That absolutely guarantees the clamping force. But clamping force on a dirty joint is still a highly resistive joint. How does the PFMEA control the surface prep before the bolt is even inserted?
Standard operating procedure dictates strict tribological controls. The connection faces must be mechanically polished on the line to remove any ambient oxidation layer that might have formed during shipping from the supplier.
They scrub it clean.
And immediately after polishing, operators apply a dedicated high-current anti-oxidation conductive paste. This paste serves two functions. It prevents oxygen ingress, and it fills in those microscopic valleys between the asperities with conductive material, lowering the baseline contact resistance even further.
And once it's polished, pasted, and servo-torqued perfectly, they apply a visual poke yoke, right? A mistake-proofing step.
Yes. The operator physically applies a torque seal marking paint, striking a continuous colored line across the bolt head and the fixed bus bar.
So if it moves, you know.
Exactly. If that bolt ever suffers from thermal shear relaxation and backs out even 1 single degree of rotation over the next 10 years, that brittle paint line will crack and visually misalign. It converts an invisible micro-rotation into an immediately obvious visual failure for any future diagnostic technician.
It is an obsessive level of process control.
Yeah.
But the final safety net on the factory floor is the end-of-line, or EOL, testing. Before the pack is sealed and shipped, they don't just rely on the fact that the machines did their job. They actually verify the physics.
100% of the high voltage connections, every single laser weld, every bolted bus bar, every contactor must undergo high precision EOL scanning using a microometer.
And measuring something down to the micro-ohm level isn't as simple as touching two standard multimeter probes to a piece of metal, right? Because the resistance of the probes themselves would throw off a reading that small.
Exactly. Standard 2-wire multimeters are useless here. They utilize a 4-wire Kelvin resistance measurement technique.
How does that work?
It uses 2 wires to inject a highly precise, known test current across the joint and a separate, dedicated set of 2 wires to measure the voltage drop directly at the connection points. This entirely eliminates the resistance of the test leads and the contact resistance of the probes themselves, isolating the true absolute resistance of the weld or bolted joint.
And the passing criteria they are looking for is aggressively strict. The source document says the contact resistance must be less than 0.05 millionths, 500ths of a single million.
They're basically zero.
That is essentially proving that the joint is electrically indistinguishable from a solid, uninterrupted block of copper.
Exactly. If a laser weld suffered from that plasma keyhole collapse we talked about and formed a microscopic void, the 4-wire Kelvin measurement will detect that the resistance is, say, 0.08 milliamps.
And it fails.
And the pack will be flagged and rejected before it ever leaves the facility.
Okay, so we have theoretically perfected the design in DFMEA, and we have ruthlessly enforced the assembly in PFMEA.
Yeah.
The battery sitting at the end of the line is flawless today.
Today, yes.
But the final question automotive engineers must answer is, will it remain flawless after 10 years and 300,000 kilometers of real-world abuse?
Which brings us to the final and, frankly, the most destructive phase of the engineering life cycle DVP&R, Design Verification Plan and Report. This is mass production validation. Engineers must physically prove that their perfect calculations survive reality.
Let's start with validating the brain, the AKF software algorithm. How do they prove the math actually works outside of a computer simulation?
Through dynamic pulse testing, often referred to as HPCC testing. They place physical battery modules inside massive environmental thermal chambers.
The torture chambers.
Literally. And they don't just test at comfortable room temperature. They soak the pack until the internal core temperature reaches -30 degrees Celsius. Then they test it. Then at +25 degrees. And finally, they bake it at +55 degrees Celsius.
And while the pack is soaking at these extremes, they subject it to massive dynamic loads.
They utilize industrial battery cyclers to inject violent 600-amp current pulses into the pack, simulating repeated maximum torque acceleration events.
Just flooring it over and over again.
Exactly. And while this is happening, laboratory-grade instrumentation is independently recording the true physical internal resistance. The validation criteria dictate that the BMS algorithm's real-time calculated resistance must stay within a strict ±5.0% error band compared to the true laboratory measurement.
So the car's math has to match the lab's math.
Regardless of the temperature extreme or the noise introduced by that massive 600-amp pulse.
So if the matrix math breaks down because the electrolyte is too sluggish at -30 degrees, the software fails validation. And it's not just accuracy they're testing, it's speed.
Right.
Yes, the diagnostic reaction time is strictly bound. The software must confidently detect a true 50% resistance spike, filter out all the inverter noise, and confirm the fault within exactly 15 seconds.
Wow. Okay, so that proves the software works. Now, how do they prove the physical hardware, those silver-plated bus bars and laser welds, can actually survive a decade of driving?
Through incredibly aggressive vibration and thermal shock profiles, this is accelerated life testing. They bolt the entire heavy battery pack to a multi-axis 3D random vibration table.
A giant shaker table.
This shaker table is programmed with specific power spectral density, PSD, profiles that simulate worst-case real-world road conditions, cobblestones, deep potholes, continuous harmonic resonance from the highway.
And they don't just shake it at room temperature, do they? The shaker table is built inside a massive climate chamber.
Yes. While the pack is undergoing continuous violent 3D vibration, the chamber is rapidly cycling the ambient temperature from -40 degrees Celsius up to +85 degrees Celsius.
So they're freezing it, boiling it, and shaking it to death all at the same time.
They are intentionally inducing extreme rapid CTE mismatch expansion and contraction while simultaneously subjecting the joints to high G mechanical fatigue.
And how long do they do this for?
They run this combined thermomechanical profile for 300 continuous hours.
300 hours. That's nearly 2 straight weeks of relentless physical torture.
At the end of the 300 hours, they pull the pack off the table, physically tear it down, and run those 4-wire Kelvin microometer tests again.
On every single joint.
On every joint. The validation criteria are absolute. After a simulated lifetime of abuse, every single joint must still measure under that 0.05 milliohm threshold. Furthermore, the torque seal paint lines on the bolted connections must be visually intact, proving zero angular relaxation occurred.
The hardware must be essentially invincible. But what about the factory processes themselves? How do you validate that the end-of-line scanners are actually catching defects and that the lasers are operating predictably?
Oh, they don't leave that to chance. The DVP&R protocols require intentional defect injection to calculate statistical process capability.
They make bad parts on purpose.
Yes. Engineers will intentionally detune the laser welding parameters on the actual assembly line, like lowering the peak power or slightly altering the focal point to intentionally manufacture bad welds with those microvoids we talked about.
Oh, to test the safety net.
They feed these known defective modules through the production line hidden among good ones to prove that the microometer EOL scanners successfully intercept 100% of the failures.
It's an active physical calibration of the safety net.
And they use this data to calculate the Process Capability Index, what's called the CPK. For critical manufacturing steps like laser weld depth and spot position, the CPK must be greater than or equal to 1.67.
What does that number mean in the real world?
Statistically, a CPK of 1.67 means the process variation is so incredibly tight that the theoretical defect rate is less than 1 part per million.
Less than 1 in a million.
It proves the manufacturing line is statistically in absolute control.
Which brings us to the final, ultimate system-level validation, the 2-second limp home test, also known as FTTI fault-tolerant time interval validation.
This is where everything converges: the software detection, the CAN bus communication, and the VCU torque derating. They place a fully functional vehicle on a dynamometer chassis and run it at simulated highway speeds under heavy load.
Okay, so the car thinks it's driving 75 down the highway.
And then the engineers artificially inject a massive hardware fault. They essentially flip a physical switch to instantly introduce a 60% resistance spike into the high voltage loop.
Perfectly simulating a suddenly cracked busbar weld at highway speeds.
Exactly. The FTTI clock starts the exact millisecond the resistance spikes. First, the BMS has that 15-second window we mentioned to correctly identify the fault, reject the electrical noise, confirm it's not a false positive from the cold, and trigger the active DTC P0AC4, illuminating the malfunction indicator on the dashboard.
But the critical safety interval, the really dangerous part, happens right after confirmation, doesn't it?
Yes. From the exact millisecond the BMS confirms the fault, the entire vehicle architecture has exactly 2.0 seconds to execute the Level 2 SOP derating.
2 seconds.
Within 2.0 seconds, the VCU must clamp the charge and discharge limits down to that 30% to 50% window.
And the pass criteria isn't just that the power drops, right? It's how the power drops.
But dynamometer heavily monitors the longitudinal acceleration metrics of the vehicle. The torque reduction must be flawlessly smoothed out. The specification strictly limits what we call torque jerk.
So you don't lose control of the car.
If the torque drops too violently, destabilizing the vehicle's simulated traction, say, simulating a spin-out on wet pavement, the test is a failure. The driver must experience a smooth, highly controlled, deterministic loss of acceleration. This allows them to maintain absolute steering control while the voltage is stabilized and thermal runaway is safely prevented.
It is genuinely staggering. Just the sheer magnitude of multidisciplinary engineering required to support a single line of diagnostic code on a dashboard. We have traced the physics from the thermodynamic sluggishness of ethylene carbonate at -30 degrees to the plasma keyhole dynamics of a laser weld, all the way up to the complex matrix mathematics of an adaptive extended Kalman filter filtering out inverter noise.
It's an entire universe of engineering.
We have seen how finite element analysis designs microscopic bumps on silver-plated copper, how servo-newtrunners measure the exact yield angle of a steel bolt, and how 3D vibration tables attempt to tear it all apart over 300 hours.
And all of this immense effort, the millions of hours of simulation, coding, and destructive testing, is entirely orchestrated to understand, predict, and control one specific mathematical threshold, P0AC4.
The next time you see a vehicle reduce its power, or you hear discussions about the reliability of modern EV architectures, you now understand the invisible reality. It isn't just a simple analog sensor flipping a switch. It is a highly advanced, continuously adapting computational model backed by statistically perfected hardware, fighting to manage the fundamental laws of chemistry and physics in real time.
It is a marvel, but before we wrap up, I do want to leave you with a conceptual pivot, a final provocative thought from our sources to really consider.
Okay, let's hear it.
Throughout this entire deep dive today, we have focused exclusively on global battery pack resistance. P0AC4 is a macroscopic metric. It represents the total systemic fatigue of the entire high-voltage loop.
The entire system choking under the load.
Right. But consider how this vast diagnostic and functional safety architecture must fundamentally change when faced with a localized microscopic failure.
What do you mean?
Well, what if the overall global resistance of the pack is perfectly nominal, the common filters are happy, but deep inside the pack, just one single isolated cell begins to violently self-discharge due to, say, an internal dendrite short?
A severe cell imbalance. One bad apple in a barrel of thousands.
Exactly. The diagnostic codes for severe cell inconsistency, like BMS-00WINFI, represent a completely different functional safety challenge. How does a BMS isolate the thermal signature of one failing cell out of thousands?
Oh, wow.
And think about the failsafe. Does the 30% limp home duating strategy still make sense in that scenario? Or does pulling any current through a shorted cell guarantee thermal propagation?
It fundamentally flips the entire safety philosophy on its head. You are no longer managing a tired, high-resistance system. You are trying to quarantine a localized catastrophic failure before it spreads to the rest of the pack. I challenge you to think about how you would redesign the software algorithms, the contactor logic, and the structural hardware to manage that one bad apple scenario compared to the global fatigue we explored today. It is a completely different, immensely complex engineering puzzle.
It really is.
We want to thank you for joining us on this incredibly dense, highly technical journey today. We started with a simple question about a sudden loss of highway power, and hopefully we've illuminated the massive, invisible engineering matrix working tirelessly beneath the floorboards to keep you safe. Keep questioning the physics behind the technology, and we will catch you on the next deep dive.